Hello, and welcome to the Houdini Fundamentals Collection, Volume 2. I'm Andrew Lowell, and this collection focuses on rigid body dynamics. It's one of the best ways to get up and running with Houdini simulations, and there's been a lot of great innovations in the last few versions of Houdini. And I really want to be able to dive in deeply and understand what's going on. And once you really understand what's going on, then you can use all the advanced features and apply them in complicated pipelines and anything else you might want to do. Just maybe produce great work. So here, I want to hit on two examples in the first lesson. And it's really just going to highlight exactly what these rigid body dynamics are doing in two things that are fairly difficult to do without Houdini's procedural environment. For the first example, let's actually take a look at the input to a rigid body simulation, and that revolves around the name attribute. So here what I've got is just making two planes, two thin collider boxes, and the idea is these little shapes are going to bounce up and down between these two things. And this assemble node is assigning a name attribute at the point level. Okay, so let's break off this example. Control C, Control V. And here we just have two arbitrary pieces of geometry. Okay, these objects are just going to use these as colliders. They're going to be static colliders. I'm going to use an assemble node. And this is going to look at what polygons are connected to each other and then assign a name attribute. And then it'll create a packed geometry. It's basically like chunking all these polygons together and putting them into a single entity, a single point with a primitive attached to it, a packed primitive. And I'm just going to call this name attribute ground underscore. Okay, so now we have ground 0 and ground 1. And that's all you really need to do with a static collider. Next, we have these wiggly boxes. And feel free to take a look inside this subnetwork to see how I made these things, but that's not really the point of the example. The point of the example is the fact that we can view these things all kinds of different ways. So we could view them as individual boxes. We could view them as an entity or a string of these boxes in combination with each other, or we could view it as a whole. We could view this all as one piece of geometry. Now, to us humans, this might look like, okay, yeah, obviously these should be separate objects, but to the computer, that's not so obvious, and we want it that way because we want flexibility and control over our setups and the ability to trick the setups into giving us the results we want. So what I'm going to do here is I'm going to call attention to these two attributes that I've assigned in the subnetwork. There is a point attribute present on each of these things for the line ID. And each one of these little wiggly worms here will have a different line ID. Line ID 1, going down farther, line ID 2. There's also a point ID, and that would represent each box that I made a copy of. Okay, so each one of these has a different point ID, but the same line ID. Okay, so we can assign the name attribute at the polygon level, attribute create. Okay, I'm actually going to leave that at point right now because these are point attributes reading in. So attribute create name. Okay, there's the name right there. We're going to switch that from a float to a string. Okay, and then I'm going to say at pt underscore id, and I'm going to enclose that with backticks. Okay, and now even though this looks like a number, it's actually a character. It's actually a string, and then we can call it box underscore. Okay, so now we have box 1, box 2, box 3. It's living on the point level, and that's not what Dynamics wants. Dynamics wants it to live on the surface, and that just makes sense because Dynamics is all about collisions with the surface. So I'm going to use an attribute promote from point to primitive, first one it finds, and we're going to promote the name to a primitive attribute. So now that's in here. Box 1 for each of the first box, box 2 for the second box, box 3 for the third box. And that's what we really need to get into dynamics here. These are all ready to go. All right, so now I'm going to make a DOPS network. Maybe put this one into the first input and this one into the second input. And that's not a requirement. We can reference these things from anywhere, but it's just good workflow to connect the wires, I think. All right. So now let's set up our simulation. So for the ground, I'm going to do a packed object, an RBD packed object. Okay, and here for the geometry source, what I want to pull in, that's going to be the first context geometry. And now you can see we have that. Okay, it's brought it in. And more importantly, if you look into the geometry here, each of these is going to be recognized as a separate object because it has that name attribute present on the point level. Right there. Okay, so that's all we really have to do with the packed object, and this is a very optimized object. Okay, we'll call this ground. And it's very important to check to see if the collisions are functioning properly, because let's say we had just this whole thing as a collision, a whole thing as a box. Well, that's not what we want. So going over to bullet data, show guide geometry, and I actually don't want to display the geometry. I just want to display the guide geometry. And there we see it. So now we know our collisions are functioning properly. Okay, I'm going to turn that off, and now we're not seeing anything, although they're still able to be collided with. Okay, so now let's read in the boxes. So I'm going to do an RBD fractured object. Now, this isn't quite as fast as the packed object, but it might be easier to work with for what we're about to do. It's still using bullet. So for the stops path, I want whatever is connected into the second input of my simulation. So I'm going to enclose this in backticks to evaluate as an expression, and I want to use the op input path. Op input path. I want .net1, which is represented by dot, dot. And then I want the first input index, which is actually the second input. Okay, so now that's getting whatever is connected into my second input of .net1, and we've found the attribute promote. There we go. And if we look at that, we've got all of our objects in. And each one of these objects is represented in my geometry spreadsheet. Box 1, box 2, box 3, they all have their own simulation properties. And that calls attention a really important point, that yes, these are geometry, but they're not just geometry. They're much more similar to objects at the object level. They have a transform. They have, in this case, collision properties and all kinds of relationships similar to rendering properties and shaders. So each of these things has their own little identity in here. It's represented reading in, they're separated by the name attribute, fracture by name. And that's why that name attribute is so important. So I'm going to call this boxes. It's important not to think of these nodes as objects, as you might in other programs. These nodes generate objects. So these are like object generators within a procedural simulation. Okay, so we've got the boxes, we've got the ground. Let's set up a standard rigid body simulation. So I'm going to add some gravity. I'm going to add a rigid body solver. And to create a relationship between the ground and the rigid body solver, we would use a merge. This merge works differently than in SOPs. This would actually form not only the merger of the data, but a relationship between that data. So in this case, it's a collision relationship. Left input affects right inputs. And that's why it's really important not to do this. We want the ground to be connected here. And I also get asked questions, okay, so what order should these be in? In this case, it doesn't really matter. We could have, for instance, this, because this is not being solved. But generally, I would either do this or this just to keep what's being, applied forces to and solve separate from any static colliders. So hitting play, And we can see, aha, so all of these boxes are being treated as separate entities because of our name attribute. Okay, and because of that, we can apply different forces to each object. That's one of the incredible features about a procedural simulation. So let's have a little bit of fun with this simulation. I want the gravity to be switching between going up and going down fairly randomly between objects. So on this gravity, I want to make either 1 value or -1 value. So I'm going to go parameters, edit parameter interface, and I'm going to do an integer here. I'll call it sign for positive or negative. And let's add a separator just for cleanliness. Okay. So this one's either going to be positive or negative, and it's going to operate differently per object. See box 1, box 2, box 3. Each of these things would have an object ID as they're being processed. So here, by default, this is -9.8, but I want it to possibly be positive 9.8. So let's put a noise pattern on here. So I'm going to do a noise. Okay, and for the noise expression, we just need 3 floats. So for now, I'm going to use any old number for the float in X. For float in Y, I'm going to animate it. So I'm going to use $T for time. And that's really important too, because as we change our frame rates, we don't want our simulation to be changing. And then let's put any old number in here for the Z. So here I want to do a comparison to see if this is greater than or less than 0. So I'll say if this noise function is greater than 0, then 1, otherwise -1. Okay, so that should produce either 1 or -1 depending on its spot in the animation. Okay, so there it switched to 1. All right, so I'm going to copy that, and then I want to multiply this 9.8 value by paste relative references by that channel. And for this, we need to make sure that we're saying set always, because this is an animated channel. We don't want to just set it once. We want to set it every single time the simulation cooks through time. All right, so now they're either all moving upwards, or when the gravity switches, they're all moving downward. Okay, that in itself might be a little difficult to do without a wealth of expressions. We might be stuck animating stuff. But now let's take that a little farther. So now per object, I want this to react differently. So here I'm going to insert $OBJ into one of these offset fields. So let's say in the X of the noise, I'm going to do $OBJ. That's the object being processed, the ID of the object being processed by gravity 1. Okay, and we'll just offset it to where we have enough difference from object to object. So $OBJ multiplied by 100. And now the noise pattern will essentially be different for each object. And we have this. Pretty cool. As a final step, instead of per box, let's have each of these worm wires react as a whole. So here under the name, instead of point ID, I want the line ID. And you would assign these attributes further upstream as you've made copies. Okay, so now we just have box 1, box 2 through 7 here. If you wanted to, you can experiment with different numbers of these things, or noise offsets. I've put in a few things to just kind of get the familiarity with simulation. All right, so now let's see what happens. Okay, so they're reacting as a whole. And that's really one of the key components to both getting your geometry to work okay and also taking control of your simulation. One thing I'll mention is that even though these look fairly innocent, like, okay, I'm simulating, I'm good to go, we always have to check the collision geometry. And that's not under the RBD solver, which is older. It's under the bullet solver. And I'm going to say show guide geometry. And you can see it's actually not a very accurate representation of the surfaces. So if your bullet data is divided into these little chunks, I'm going to say create convex hull per set of connected primitives. And going back to the first frame, it's initialized to be a much more accurate simulation. And this can even be quicker than concave. In fact, I'd highly recommend against using a concave mesh in a bullet simulation. And there we go. So now we have nice accurate collisions, everything's ultra fast, and we're able to do different forces for objects. Let's take this idea into something that's a bit more production relevant. All right, so for the next example, what I have here is something that might be very challenging to work with, which is a very, very concave, very kind of exacting, difficult scenario. And notice that with using DOPS, this is incredibly fast to have this ball rolling down and very accurate too. Okay, it's basically real time here. All right, so how did I pull this off? And how would you work with similar situations? So let's take that same idea. So here we've just got an arbitrary terrain. Well, what I want to do is, instead of representing this as a completely concave, meaning there's indentations in it that would be hard to solve, I'm going to use the polyreduce. Let's make our own chain of events here. Okay, here's our ball, here's our terrain, Control C, Control V. Okay, so I want to take this and polyreduce. All right, and let's maybe keep about 5%. Okay, so that in itself is useful. Maybe we could get some better collisions out of this. But what I actually want to do is I want to treat each polygon as its own collider. So using a facet, I'm going to break apart the points, and these will all be disconnected polygons. So make unique points. Okay. And now I'm going to give these some depth so that they can be their own colliders. Poly extrude. Okay, so let's use the local polygon normal, and we can extrude these either outwards or inwards. I'm going to extrude them away from the surface that I'm colliding with, and make sure you enable output back. And the normals are flipped because we did a negative extrusion, so I'm going to use a reverse. There we go, just nicer to look at. And finally, the assemble from the last example. Okay, create pack geometry. All right, so now we have an object that will serve as an individual collider instead of one big, hard to compute concave object. We've got lots of little convex objects, and Bullet will love this. It will hate the alternative. Okay, so now here's a ball, and it's a wobbly ball just so we can see the accuracy of the collisions. Okay, so let's get that into DOPS once again. DOP network. Okay, we need the ball, ground. For this prefix, I want ground underscore for the name attribute. This ball, I'm going to check and see if it has a name attribute. Well, it doesn't, but we've only got one, so we don't really need it. Okay, diving in. Okay, so I just want a single RBD object. So RBD object, and let's set the path to whatever is plugged into the first input of .NET1. Let's check that out, see if it works. And notice the object name is RBD object 1. Not terribly good. We'll call it ball. Okay. Next, we want some gravity applied to the ball, a rigid body solver, and a merge. Okay, then I want the RBD packed object, second context geometry, and checking the collisions. We now have that, which is great, as opposed to the alternative, which would be one big, messy, hard to compute mesh. This will simulate nice and fast. Okay, so this will go into the left, this will go into the right, and let's watch that simulate out. Incredibly fast, incredibly accurate. And this goes to the next really big point about using a program like Houdini and proceduralism to generate a simulation is the fact that what the viewer sees that observes your final shot never is going to see what we did to this collider. And as long as you're getting quick, interactive, highly fast, iterative simulations, that's all that matters. No one has to see what we did to this geometry. Here, I'm going to dop import only the ball out of the simulation. Dop import. Okay, so we want to use this dops network, and we want to merge the object ball. Fetch geometry. Okay, so there's our ball, and that's all we have to render. Okay, we could render that as a separate object. Here's the original terrain without all the poly reduction and everything like that. And that gives us a great framework to set up almost any kind of simulation.